This is part 4 of section 3.4. On this problem, we're being asked to find a and k and then evaluate the function and round to 3 decimal places. So we're given f of x is equal to 40 plus a times 4 to the kx. We are told what f of 0 is equal to. We are told what f of 2 is equal to, and then we're asked to find f of 1. So the first thing I'm going to do is I'm going to plug in 0 for x, set it equal to negative 216, and solve. So f of 0 would equal 40 plus a times 4 to the 0 power, which is 1, so that's just a. This 4 to the 0 is 1. And this is equal to negative 216. So now subtract 40 from both sides, and you'll get that a has to equal negative 256. Okay, so now I can improve my equation because that's the first part I've gotten, and I can rewrite this now using this value. So my new and improved f of x is 40 minus 256 times 4 to the kx. And I have used this information. Now I'm going to use this and plug in 2 and set that equal to 39. So f of 2 would equal 40 minus 256 times 4 to the 2k. And that has to equal 39. Okay. Well, let's subtract 40 from both sides. I get negative 256 times 4 to the 2k is equal to, if I subtract 40, I get a negative 1. Now divide both sides by negative 256 so I can get my exponential part by itself. So I end up with 4 to the 2k is equal to 1 over 256. Okay, now it turns out that 256, its prime factorization is 2 to the 8th power. So this is 2 to the negative 8 power. And I can rewrite this 4 as 2 squared. Okay, and then a power raised to a power, we should multiply those. So I have 2 to the 4k is equal to 2 to the negative 8. And now set, because they're both base 2, set the exponents equal to each other. I have 4k is equal to negative 8. So k must equal negative 2. Okay, so I have found my a, I have found my k, so I can write my f of x with the constants in it now. So my final f of x is 40 minus 256 times 4 to the negative 2x. Okay, so my last part of this problem is to find f of 1. So f of 1, just plugging that in here, is 40 minus 256 times 4 to the negative 2, which is 40 minus 256 times 1 over 16, which is 40 minus 16. So your answer is 24. Okay, So now we've solved a whole bunch of exponential equations, and we're going to move on to logarithmic equations. So these are problems that have some sort of log term in it, okay? Now, one of the things that's added to this, difficulty that's added, is that when we're solving logarithmic equations, we can get false answers. So this is sort of like solving radical equations where you can get answers that are false or that give you a wrong answer and you have to check it, or rational equations where you have to plug in the number and make sure you're not dividing by 0. We have a limitation on the domain of a log, and the argument of your logarithm has to be greater than 0. And it is possible that we get false answers. So we will always have to check every apparent solution to make sure that we don't have a domain issue. Okay? So, just like with our exponentials, we have a couple of different ways to get these problems solved, depending on what we're given. Now, if we have a logarithmic equation and it has only one logarithmic term, or later, we can combine things and simplify them so that we only have one logarithmic term. Then we can just use the definition of a logarithm to solve it. We can change we'll get the logarithm by itself and then switch to exponential form. So let's say I want to solve 1 plus 2 times natural log of x is equal to 4. I only have one logarithm, and I want to try to get it by itself. So subtract 1 from both sides, and I have 2 natural log of x is equal to 3. Now divide both sides by 2. Natural log of x is equal to 3 halves. Now remember that natural log has an understood base of e. And so if I switch this from logarithmic form to exponential form, I end up with x is equal to e to the 3 halves power. Okay, this is your exact answer. If you want to check, you can plug that into your calculator. I'm going to store it in memory so that I have the exact answer, but while I have this number up here, they will ask for an approximation, usually on these problems to 2 decimal places. So I would get approximately 4.48, okay? But if I store this in memory and then plug it in directly here, 1 plus 2 natural log of x, which is going to be the number I just put in memory, and it should give me a 4, and that's true. Okay, so I've just done a complete check. I know this answer is correct, but also you should check to make sure that whatever value you got right here is not going to give you a negative in the argument of a logarithm. Well, I only have one log. My logarithm, the argument is x. This is x. It is a positive number, so there's nothing else I need to do. This is a good answer.